Okay, so let's talk about exponential functions. First thing we need to talk about is the definition. So the definition of an exponential function says this. An exponential function has the form y equals b to the power of x. So another word for power is exponent, right? So this actually should be no surprise of what it looks like definition. There's two restrictions on b. b, by the way, is also known as the base. So there's two restrictions on the base. One of the restrictions is your base can't be equal to 1. Because let's think about it. 1 to any power is always going to be, 1. So that doesn't do us any good. The second restriction is your base must be greater than 0. Now here's the deal. We're going to find out that this function is a one-to-one function. And because it has a one-to-one, or because it is a one-to-one function, it will have an inverse. I can take negative numbers to any power all day long. But the inverse of the exponential function cannot have the base being negative, which is why the exponential function itself can't have a negative base. If its inverse can't have a negative base, neither can the function itself, which is why the base must be greater than 0. It must be positive. Now, when we have new functions, we like to know the domain and the range of those new functions. And the best way to determine the domain and the range is by graphing. So, we're going to graph. And let me put an exponential function up for us to graph. So I would like to graph this exponential function, 4 to the power of x. Now, the best way to graph a function when you really don't know what it looks like is to create that table. So let's create that xy table. Here are my favorite numbers to plug in for x. Okay, I have some positives, some negatives, and then the neutral number. That's always good to have, right? So, not going to insult your intelligence. 4 to the power of 2, good. 4 to the power of 1, excellent. 4 to the power of 0, yep, some of you remembered 1. Anything to the power of 0 is always 1. 4 to the negative first power. Remember, anything to a negative power is never negative, ever. Anything to the negative power is never negative. In this case, it makes it the answer of 1 over 4. And to the negative power of 2, again, never negative. It makes it to the power of 1/16. Okay, so we have our table. Let's create our graph and let's see what this looks like. So, we have 0, 1, right? We have 1, 4, 2 and 16, way up there somewhere, negative 1, and 1/4, and then negative 2 and a 16th. So if I connect the 5 dots that we just got, this is what it looks like. Agreed? All right, so answer me this. Over here in the negative end of the world, if I keep plugging in numbers that are less than negative 2, am I ever going to get a negative answer? Good, you're not, because any number to a negative power is never negative, so I'll never get a negative answer. Will I ever get this function actually being exactly equal to 0? You're right, you won't. It will not be exactly equal to 0, ever. With me? So here's the deal. This end of the world, this particular graph is just skimming along that x-axis. Never touching it, never crossing it. Got it? Okay, and as I keep plugging in numbers larger than 2, this end of the world, this graph just keeps going up. Okay, dramatically, drastically, it just keeps increasing. So, remember, the whole reason we graphed this was so we could determine the domain and the range. So if I take a look, the domain, my x's, I can plug in any x value I want, can't I? So my domain will be from negative infinity all the way to, good, positive infinity. Now, let's look at your range. Your range of those y's, so when I come in from the bottom, the first y value that's not actually graphed, but where this graph bottoms out at, is actually at 0. It bottoms out at 0. It goes all the way to infinity. But here's the question. Since it bottomed out at 0, will it ever be 0? No, which is why there's a parenthesis around that range. It won't be a bracket, it'll be a parenthesis. Are you with me? Okay, so I want to take a look at another graph. So I'm going to erase this definition here so we can see a second graph. Because I want to see what happens when my base is not an integer. And you're like, okay, I have to remember what that word integer means. Yes, you do. A better way to define an integer is what it is not. An integer is not a fraction and it's not a decimal. So, this base was an integer because it wasn't a fraction and it wasn't a decimal. Got it? Okay. Now I want to see what my graph looks like if my base is not an integer. So, I have the function so my function that we're going to graph is still an exponential function clearly. The base is not an integer. I want to see what this looks like. I'm going to create a table. If you allow me, I'm just going to put my y's on this end of the world that go with this function. Okay? And these y's go with this function. Okay. So on this one, when I plug in 2, what do you get? Good. You get a 16th. When you plug in 1, you get a quarter. 0, yeah, 1. Anything to the 0 power is 1. When you plug in a negative 1, remember, anything to a negative power is never negative. So in this case, it's going to be 4. And when you plug in that negative 2, it'll be a positive 16. With me? Okay, so I am going to take graph number 2 and I'm going to put it over here on this same graph so you can see what happens. So that was graph number 1. Graph number 2. I plugged in 2 and I got a 16th, didn't I? So that's about here. I plugged in 1 and I got a 4th, didn't I? So that's about there. I plugged in 0 and I got 1. Same spot, right? I plugged in negative 1 and I got 4 and negative 2 gave me 16. So here's the deal. Let's see how my points are lining up. Well, that one was a little off kilter, so we're going to rearrange it. So the graph we just did, when I take a look at it, the question is this. As I keep plugging in negative numbers, what happens to this end of the graph? Yeah, that keeps going up, doesn't it? And this end of the graph, when I keep plugging in positives, will it ever be negative number? Nope. Will it ever be a 0? Nope. So here's the deal. It's skimming along the x-axis again. Notice the domain and the range are still the same, right? The domain is still negative infinity to positive infinity. That hasn't changed. Notice the range. The range is still 0 to infinity, excluding the 0. Are you with me? All right, so now let's take a look at this. These two graphs are a little bit different, but at the same time they have something in common. So, when my base was an integer, do you notice we got this increasing graph? Right? When my base was a fraction, notice, and by the way, this fraction, this 1/4 was less than 1. When you have the base less than 1, you end up with this decreasing graph. Cool? Understand that. If your base is greater than 1, you have an increasing graph. When your base is less than 1, you will have a decreasing graph. With me? Okay. Now, that's a major difference between the two. Now, similarity. Let's notice similarities. One similarity is the y-intercept. They both crossed at 0, 1. That's a similarity. A second similarity is a horizontal asymptote. And that just means a wall. And the horizontal asymptote is the x-axis, isn't it? So the x-axis also has another name. The x-axis crosses the y-axis, doesn't it? Through what number? 0. The x-axis is also known as y equals 0. These are two similarities, and they're two major similarities. Cool? With me? Okay, so hang in there. I'm going to do a little bit more graphing with these exponential functions, and you'll notice that when we graph these exponentials, it's almost like we were graphing the quadratics, because depending upon what number they've added and where they've added it to, it's going to start moving my graph around. Okay, so let's take a look at these two particular examples. Let's look at example number 3. So I'd like you to notice something. It is an exponential function, correct? My base is less than 1, correct? So since the base is less than 1, that tells me the graph will be a decreasing graph. Got it? Okay. Now, do you notice there's a plus 2 added on? So, question. In a previous lesson, I asked the question this way. Hopefully you remember. Is this plus 2 invading the space of x? Or is it outside of the x? Good, it's outside of the x, which means this is affecting which variable? Yes, this is affecting the y. And in this case, it's telling you that the y's are going to go up by 2. With me? The y's are going to go up by 2. That's what that is telling you. So, what's going to happen to your whole graph? Exactly, your whole graph will shift up by 2, shouldn't it? Okay, so, a couple of things. I know my domain for an exponential function is negative infinity to positive infinity. I know my range is not including the 0, but 0 to infinity. And I know my y-intercept should be at 0, 1. Now, the question is, as soon as I add that plus 2, will all of this stay intact? That's the question. So let's check it out. When we plug in 0, we get 1, don't we? Because anything to the 0 power is 1. But 1 plus 2 is 3. Yeah, so in this particular case, I'm not at 0, 1. I'm at 0, 3, aren't I? Okay, so if I plug in 1, that'll be a third, won't it? Add 2, that's 2 1/3, isn't it? So right about there. If I plug in 2, I get a 9th, correct? Plus the 2 gives me 2 1/9, doesn't it? If I plug in negative 1, that's going to be a 3. 3 plus 2, yeah, that'll give me 5. So can you see what's happening already? Let me just do one more. Negative 2, this becomes a 9, plus 2 is 11, right? So if I take a look at my graph, if I connect my dots, what I'm seeing is this. So is it a decreasing function? Check. Is the domain negative infinity to positive infinity? Check. I'm going to get back to the range in a second. Is the y-intercept at 0, 1? Oh no. The y-intercept moved to 0, 3, didn't it? Okay. Now the range. Question. And the way I drew it, some of you are like, well, obviously it doesn't start at 0. If I plugged in a 3, 1/3 to the power of 3 is 1/27 plus 2. So that's 2 1/27, right? Anything you get here, you're going to add 2, aren't you? Which means you're going to get 2 and something. This graph doesn't bottom out at 0. This graph bottoms out at 2, which means your range has now moved up 2 spaces also, as well as the y-intercept. The domain didn't change, decreasing didn't change, but the y-intercept and the range, which both deal with y's, have been affected. With me? Okay, let's look at problem number 4 over here. So, I want to graph it. Now, this tells me, my base tells me that it's increasing because it is a greater than 1 base. Agreed? This over here is outside of the x's, again, which tells me it affects the y's, which means in this case, what's happening to your y's? Yeah, they're going to go down by 3 spaces. Are you with me on that? Okay, so here's the deal. Do you think the domain is going to be the same? Yes. Do you think the range is going to be the same? No, because if the y is being affected, the range deals with the y's, so the range is going to be affected. Do you think the y-intercept is going to be the same? No, because same thing. This deals with the y. It's a y-intercept. So check it out. When I plug in 0 into x, I get 1, don't I? Well, what's 1 minus 3? Yeah, -2. So there's my y-intercept now. My y-intercept moved down to 0, -2. It moved down 3 spaces. It should have been right here. This is where my y-intercept should have been based on my previous 2 graphs. Based on problems number 1 and 2, that's where my y-intercept should have been. That's the parent graph. But as soon as I tacked on this -3, or even this +2, the y-intercept moved. Good? Okay, now the range. The question is, does the range still bottom out at 0? Don't think so, because any number you get here, you're going to -3 from it, aren't you? All right, so if you plug in, let's say 1, 5 to the power of 1 is 5, -3, 5 minus 3 is 2. Got it, just checking. Let's see, we plugged in 1. Sorry. If I plug in 2, that's 25. Okay, so this is supposed to be an increasing graph. Let's check out when you plug in -1. 5 to the -1, 1/5, -3. Yeah, that's like a -2 and 4/5. So here's the deal. I am going to get rid of this guy because he's in my way of my new graph. Because I want you to see this. Your graph will be increasing, but now it's bottoming out at -3. Got it? Okay, so just like the parabola, when you have a number tacked on outside of the x, it's affecting the y's, which means the whole graph is going to shift either up or down, which is going to affect your range and as well, in this case, your y-intercept. Good? Okay, hang in there. Got a couple. Okay, so let's look at some more graphing problems. Let's look at number 5. Now, do you notice in this case, my base is greater than 1, right? Which means this base tells me my graph will be an increasing graph. Now, do you notice in this case the -3 actually moved into the house of x, right? So it's going to affect my x's, which means it's either moving left or right. And a quick refresher to determine which way. You have to take this parenthesis and you must equal it to 0 to determine which direction this is going. Since I solved for x and I got a +3, this tells me that my graph is shifting to the right 3 spaces. Cool? Okay, so remember, your domain on a typical graph is -infinity to +infinity. Your range is supposed to be from 0 to infinity, and your y-intercept is supposed to be 0 and 1. The first 2 graphs told me that this is what or how an exponential graph behaves before we tacked on any numbers. Now, let's see what happens in this case. So let's start thinking about it, all right? Let's start shifting things around. I don't want to create a table. Let's see if you're following what's going along, because this is exactly the same thing that happened when we graphed all those parabolas before. All right? I am going to plug in 0 though. So 0 for x. Or pardon me, my goof. Plug in the 3 for x. 3 minus 3 is 0. 2 to the power of 0 is 1. So now when x equals 3, I get y equaling 1. Are you with me? Okay. It didn't shift up, it didn't shift down. So even though my graph is shifting to the right, is the domain going to change? No, the domain is going to stay the same. This graph will be an increasing graph, but instead of crossing here at 0, 1, my graph or my y-intercept has shifted, and it's no longer a y-intercept. And I don't really care that it's not a y-intercept. As a matter of fact, I don't really care what the y-intercept was. All I care about is where did the 0, 1 point move? Well, remember, you had to plug 3 in to make this parenthesis equal to 0 again. And 2 to the power of 0 was 1. So this y-intercept moved over to the point 3, 1. That's where it moved. I don't care about that it's not a y-intercept. I don't care that it's not a y-intercept any longer. What I want to know is where did the y-intercept go? That's what I want to know, because that's my key point. The y-intercept is my key point that helps me figure out what this graph is looking like. Because right about here is where it starts climbing quickly. With me? Is the range still 0 to infinity? Yes, it is. Okay, because it didn't shift up and down, it just shifted left and right. And in this case, shifted to the right 3 spaces. Good? Okay, look at problem 6. So let's talk about this one a second. My base is less than 1, which means I'm going to have a decreasing graph, aren't I? Do you notice this minus 4 at the end? Affecting the y's, which means my y's are going down 4 spaces, aren't they? Do you see this parenthesis? A plus 1 moved in, didn't it? Well, remember, take that x plus 1, set it equal to 0, and solve. And in this case, my answer is a negative 1, which means my graph doesn't just move down 4, it moves left 1 space also because of this work. So, here's what you're telling me. My 0, 1 point, it's no longer at 0, 1. This is now going down 4. So, 1, 2, 3, 4. And it's going left 1 space. My 0, 1 point is moving. Down 4, left 1. This point is now the point negative 1, negative 3. So the y-intercept moved to negative 1, negative 3. I don't care that it's not a y-intercept any longer. I want to know where it moved. It's moving down 4 spaces, which means my horizontal asymptote, right? Remember that horizontal asymptote we spoke about before? Used to be the x-axis, but when it shifted down 4 spaces, it's right here now. So this is at y equaling negative 4. And this is a decreasing graph, isn't it? Well, right about here is where the sketching of this is going to happen. So, based upon the fact that numbers move into x, or numbers affect the y's, tells you if the graph shifts up or down. By the way, there's one thing I didn't talk about, but you'll know it. What happens if there was a negative in front? Yeah, this whole thing would flip over. Okay, so it would see its mirror image below here. So now it would do this number instead. Cool? Okay, so hang in there. I'll be right back with some more exponential function stuff. Okay, so let's talk about 2 types of bases that we will work with quite often. One is known as a common base. The other one is known as a natural base. Now, the common base is based on our number system. And our number system is based on one number, 10. Every place that we deal with, every place value we deal with in our number system is based on 10. We have the ones place. Well, that's 10 to the 0. We have the tens place. Well, that's 10 to the first. We have the hundreds. That's 10 to the second. With me? We even have the tenths place, which is 10 to the negative 1. Our whole number system is based on 10. The common base is 10. Good? There's another base that we deal with quite often, and that base is e. Now, e may look like just a variable to you, but e actually represents a number. So, here's going to lead me into something that I want you to get your graphing calculators out for. Let's see. We're going to find the value to 4 decimal places. And the first thing we're going to figure out is e to the power of 1. So in your graphing calculators, you have an ln key, and above it is the e to the x key. So go find that on your calculators and punch that in for me, e to the power of 1. And I need you to round it to 4 decimal places. What do you guys get? Okay. Hopefully we agree. I got 2.7182. Good? All right. This is what E represents. E is this decimal, but you don't need to remember it. Why? Because it's programmed in a calculator. So understand that every time you see an E, it is a base that is greater than 1. Which means if you are graphing it, it's going to act just like all those other graphs we dealt with just before this, where the base is greater than 1. Cool? Okay, so got some more examples I want you to get your graphing calculators out for. We're going to figure out e to the power of 6. We're going to figure out 1/3 to the power of 0.25. And we're going to figure out 2 to the negative pi power. Okay, so give you a few moments. You guys punch these into your calculators and hopefully we agree. So let's see if we do. For number 2, 4288. So this is what I got for e to the power of 6. Hopefully we're agreeing. So let's look at this. 1/3 to the power of 0.25. I ended up with 0.7598. Hopefully we agree. And last but not least, be careful when you punch in number 4. There's a negative in front of that. Remember, on the graphing calculator, there's this little negative key at the bottom next to the equal to key. This is your negative sign. If you hit the subtraction sign instead of the negative sign, it won't work. It'll give you an error. So please be careful. If you need a negative sign, this is right next to the equal to key. That's what you're looking for. So I ended up with approximately hopefully agree with these place values. Understand again, 2 bases that we will deal with quite often. A common base of 10, the natural base of e. Good? Okay, hang in there. Got just a few more problems to work on. Okay, so now let's talk about solving exponential equations. I'm going to put a problem up here for us to solve. And yes, I know you already know the answer to this problem. It's a very easy problem. Well, you know what? In order to understand how to solve these, we need to understand how to solve the simple ones. Because when we understand how to solve the simple ones, we'll understand how to solve the ones that are not so simple. So, here's the deal. The key to solving exponential functions, majority of the time, is to make sure your bases are exactly the same. On the left side, my base is a 3. On the right side, it's a 9. Can't I turn a 9 into a 3? Yeah. So I could rewrite the problem as 3 to the x equals 3 to the power of 2. Agreed? Well, if these two sides are supposed to be equal, and the bases are already equal, then the exponents don't have a choice. The exponents must also be equal to each other. Are you with me? If the bases are already equal and these two sides are supposed to be equal, then these powers don't have a choice. X must be equal to 2 in this case. Are you with me? Okay. And that actually would be your answer, which is the answer you knew it would be already. You knew 3 to the power of 2 was 9. So what I gave you was not a big deal. But to solve an exponential function, the key again is to get the bases the same. So let's look at another problem. Oops, 16. Okay, so this is an exponential problem again. Notice, I'm trying to solve for x and it's in the power position again, just like problem number 1. Remember the key, you need to get the bases the same. I have a base of 4 and a base of 16. And when trying to get the bases the same, you're looking for a number that's equal to the smaller of the two numbers is what you're looking for. Or you're going to have to break them both down because that happens too. But let's stick with this problem. So I can change a 16, can't I? Yeah, I can change a 16 into 4 to the power of 2, can't I? So again, notice the bases are the same, aren't they? These bases are the same, which means your exponents don't have a choice. Your exponents must also be the same, which gives me a nice little equation to solve in this case, which tells me x must be equal to a -1. And when I plug -1 in here, what's -1 plus 3? 2. And you know 4 to the second is 16, don't you? Okay, good. With me? Got another one for us. Okay, so how lovely is this problem? Well, I'm solving for x and it's in the exponent position. With me? So I'm trying to get the bases the same, which is what I did in problems 1 and 2. But here's the question. 9 is the smaller of the two bases, right? Can I turn a 27 into a 9? Remember, I need to think powers. 9 was rewritten as 3 to the power of 2. 16 was rewritten as 4 to the power of 2. Can the 27 be rewritten as 9 to some power? No. So in this particular case, I cannot rewrite the 27 in terms of 9, the smaller of the two numbers, which means I need to change both of these. I need to rewrite them into a different base altogether. So, gotten any ideas? I hope you're thinking to yourself, well, 9 is 3 to the second. That's good. So can I rewrite the 27 in terms of a 3? Good. You're like, well, 27 is 3 to the power of 3. That's good. But you still have this 2x plus 3 outside, don't you? Okay, so this side is still 3 to the second. Now let's look over here. What happens between parentheses? I have this 3, and then I have a parenthesis, and then I have this. What operation do you do between them? Excellent. You multiply, which means on the left side I have 3 to the power of, that's right, 6x plus 9. Remember, through parentheses, this is a distribution problem. So, are my bases now the same? Yes, they are. The bases are now the same, which means, that's right, the exponents must also be the same. They must be equal. They don't have a choice. So as we solve this, you're going to notice that you're going to get an answer that was not very obvious. You're like, I never would have even thought about -7/6. And that's right, you wouldn't have. This is why it's important to understand how to solve exponential functions. Or equations, I should say. Good? Okay, hope this helped. You have fun with this stuff, and I'll catch you on the